So let's look at another circuit here. And we're going to use reduce and return for this circuit as well. So just kind of start looking away from your source. So we've got the source here in the middle. So I would probably start looking on the outside of the circuit to determine where I'm going to make my first reductions, right? So for let's look over here at R1, for instance. R1 looks like it's actually in series with R2 and R3. Why is that? It's because it looks like the current that would go through R1 would have to continue through R2, would have to continue through R3. There's no other place for that to go. So if we add those together, that would be 24 kiloohms. And so if you can see down here a little ways, those are already combined here in this second step. Okay, so there's the 24 volts, right? 24 kiloohms right there. And it actually is in parallel with this 24 kiloohms. And those are both in series with the 12. Looking on the other side, we see that we've got our 8 and our 9 in series with each other, and that's 9K. And that is in parallel with my R7, which is 9K. So when we redraw this circuit, what it really looks like is going on is this, after we make our adjustments there for those series resistors on each end. Now at this point, we can combine our parallel networks here and redraw our circuit. So here, this would be, let's call it RA. We have this resistance in parallel with this one, so 1 over 24K, 1 over 24K. That would give us 12 kiloohms there. And then we have R7 and R8 and 9 in parallel. So RB would be 1 over 9K plus 1 over 9K, which is 4.5 kiloohms there. All right, so if I redraw, and that's going to be step 2 for us. So I'm going to redraw. So I've got 4.5 kiloohms that I found here, 12 kiloohms that I found here. Clean it out just a little bit. 4.5K. And then the 12 kiloohms, I haven't done anything with that. And the 12 kiloohms here. And 72 volts here. And let's move that down just a touch. Okay, so for this circuit, and that'll be our third circuit, I see that my resistors over here are in series, and these are also in series with each other. And then they'll be in parallel. So I'm going to take it one step at a time here and say that that's 24K. And here we have 16.5. All right. I think I've left off my ground here. So that's the fourth circuit in my reduce portion. And then I'm just going to combine the two parallel resistors into an RT. So RT here will be 1 over 24K plus 1 over 16.5K. So that'll be about 9.78K. So my final most reduced circuit has about 9.78 kiloohms of resistance for my 72 volt source. And that's the fifth and final reduced circuit. Now I do that so I can find my source current, which is E over RT. So I've got 72 volts over 9.78 kiloohms, or 7.36 milliamps of current right here. And remember, we've got 72 volt drop across that 9.78 kiloohms. And I can step back. That 7.38 milliamps is right here at my source. And now that I've split the 24 and the 16.5, each of those see 72 volts drop across them. So that will allow us to find our currents. So that will be 3 milliamps. And the current through the 16.5K. Should be 4.36, 4.38, depending on how we actually round in a few of these places. Oh wait, that's 7.36. I think I drew it wrong there. Okay, so for step 4, we have all of our voltages and our currents. And I'm just going to take a step back up and copy everything back up. So we've got 7.36 milliamps here, 3 milliamps this way, 4.36 milliamps this way. And now we'll find our voltage drop. So when you're looking at something that looks like a ladder circuit, you do a lot of on the return, find current, find voltage, find current, find voltage, find current, find voltage. You kind of go in and out of that process. Okay, so 3 milliamps through 12K ohms of resistance means that I've got, that's current times resistance, or 36 volts there. I'd also have 36 volts across the next 12K because I've got the same current through the same amount of resistance. So I could do this equation for both of those resistors. And then on this side, I've got my 4.36 milliamps of current through 12K ohms of resistance. So my voltage drop there would be about 53.52. I'm having trouble reading my own writing here. 52.32, I believe. And then my voltage drop here, the 4.36 milliamps times 4.5K ohms, and that would be 19.62. Should be 3.2 and 6.2. I must have rounded a little bit differently there. Actually, let me just check real quick. 4.36 milliamps times 12, 52.32. 4.5 times 4.36, 19.62. Okay, so it's just going to be a little shy of the 72 volts on that side, probably due to some rounding somewhere elsewhere. All right, so let's take what we've learned here and step up one more level and transfer everything we've learned here up to this circuit. So we know we've got from the source 7.36 milliamps we know this way we've got 4.36 milliamps, and this way 3 milliamps. What else do we know? We know some voltages. We know we've got 36 volts across here and across here, because remember the 224K ohm resistors up here combined in parallel to be the 12K down below, and that means they're in parallel, so they have the same voltage drop across each. And over here we've got that 52.32 volts, and then the 19.62 volts right here. And so what this will allow us to do, and I guess I can write these in as well. That's 4.36. Well, let me move it over so we don't confuse that with anything else. 4.36 milliamps here and 3 milliamps here, which combine to be our 7.36 milliamps there. Just writing it in a couple different locations. All right, so what we are missing here is the current through here and here. But we know we've got 36 volts across 24 kiloohms of resistance. So that's going to give us 1.5 milliamps here. And we also have 36 volts across this 24K ohm resistor R4, which is also going to see 1.5 milliamps. So that 3 milliamps coming in is going to divide equally across those 24K ohm resistors, and then it'll come back together over here. So we've got that 3 milliamps back through the 12 there. Now what happens here on the other side, we've got that 4.36 milliamps coming in to our node here at R7 and R8 and 9. And it's going to divide. Now, we know we've got 19.62 volts across each, divided by 9K. We would see 2.18 amps this way, and 2.18 amps this way. Now, the only reason we have an equal amount of current through R7 that we do through R8 and 9 is because they're both 9K ohm resistors. If they were different, we would have a different amount of voltage through current through each. Okay, so now we're ready to go back up to our original circuit and draw in everything we have learned. We're going to not have a lot of room up here, so I'm not going to draw maybe everything, but this should be 7.36 milliamps here, 4.36 milliamps here, 3 milliamps here. And now remember, I have 1.5 milliamps through here and 1.5 milliamps through here. And on the other side, I've got my 2.18 here and here. I'm also going to draw in all of the voltage drops that I know, 52.32. This is my 36 volts. Through R4 is also 36 volts. And then through here, R7 is still the 19.62 volts that we had before. All right, so what do we not know? We don't know our voltage drops here, here, and here. And we don't know our voltage drop here and here across R9. So, but we do know the currents through those resistors, so this really is no problem. So for R1, we've got 1.5 milliamps through 4K ohms of resistance. So at that point, we should have 6 volts. And we've got that same 1.5 milliamps through R2. So multiply that by your 8 kiloohms, and we get 12 volts there. And then the same 1.5 milliamps through R3. Again, they're all in series, so they all have the same current through them. So 1.5 milliamps through R12K would be 18 volts. And notice the 18 and the 12 is 30 plus the 6 is 36. So those three series resistors divide that 36 volts down into voltage drops that are proportional to the amount of resistance that we have. And then on the other side of the circuit, R8, we've got 2.18 milliamps through 3K ohms of resistance. So that must mean we have about 6.5 volts there. And then the same 2.18 amps of current, milliamps of current through R9 times the 6K would give us about twice that. So it should be about 13.08 volts there. So now for our ladder circuit, we know all of our voltages and all of our currents. Now you can work some examples and go back through any of the videos that you need a little extra help on.